So let's take a look at the binomial series. So let's say we have the binomial 1 plus x raised to a certain power k. Now in the binomial series, k has to be any real number, and so using Taylor polynomials we can expand it into 1 plus k times x plus k times k minus 1 times x squared over 2 factorial plus k times k minus 1 times k minus 2 times x cubed over 3 factorial, and so forth. And so the binomial series for this, the series notation, is going to be equal to the infinite series from n equals 0 to infinity. Now we have in parentheses the k value on top and the n value on bottom times x to the n, since there's just a positive x here. And so what we have to do with the binomial series is take a binomial, expand it using this formula, and then rewrite it as a power series. So let's say for number 1 we have the square root of 1 plus x, and we have to turn it into a power series. So very first thing is to get 1 plus x, or the square root of it, to look like 1 plus x to the k power. So we can simply just turn it into 1 plus x raised to the 1/2 power. So notice 1/2 is going to be the k value. So if we were to rewrite this as a binomial series, we have the series from n equals 0 to infinity. Remember, the k is going to be on top in parentheses, so 1/2. We have the n on the bottom, and since we just have a positive x, we can write it as x to the n. And so now what I have to do is expand it using the formula. So obviously the very first term is going to be 1, and then we have plus k, which is 1/2 times x, plus k, so 1/2 times k minus 1, so negative 1/2, times x squared over 2 factorial, and then plus 1/2 times k minus 1 negative 1/2 times k minus 2 negative 3/2 times x cubed over 3 factorial, and so forth. And so now what we have to do is simplify the expression and recognize patterns so that we can come up with a power series and rewrite it as a power series. So I'm just going to go ahead and write the first term down, so 1. And then we have plus x over 2, or half x. And then for this one, notice there's a negative, so I can bring that out front. And then we have 1 times x squared over, now we have 2 times 2, which is 4, but I'm going to rewrite it as 2 squared times 2 factorial. And the reason why I'm doing this is so that I can recognize patterns and then rewrite it as a power series. And so for the next one, the negatives will cancel, so we have a positive, and then we have 1 times 3 times x cubed over, now there's 3 2's, so it's going to be 2 cubed times 3 factorial, and so forth. And so as you look at this, realize that there are patterns. So that starts from 2 to the first, and it goes to 2 squared, then 2 cubed, and then goes to 2 factorial, to 3 factorial, 4 factorial, and so forth. And then we have 1 times x squared, 1 times 3, the next one will be 1 times 3 times 5, and 1 times 3 times 5 times 7, and so forth. And we also have x, x squared, and x cubed. So these first two terms don't necessarily follow the patterns of these next two terms, so I'm going to leave those two outside the series when I write the power series. So we have 1 plus x over 2, and now I can write the series. So we have the infinite series. Now keep in mind we're going to start from n equals 2, and the reason why that is so n equals 0 is the first term, this one's n equals 1, the second term, n equals 2 is the third term, and n equals 3 is the fourth term. So we're going to start with n equals 2 as a third term, and we're going to go to infinity. So now the first thing we have to realize here is that there's an alternator. It goes from plus minus plus minus. And so since the first term here that we're going to start in the series is a negative, I'm going to write it as a negative 1 to the n. Now I can write plus 1 or minus 1, but I'll write minus 1, because when I plug in 2 for n, 2 minus 1 is 1, and negative 1 to the first is still negative. So I'll write it as n minus 1. And then notice we have x, x squared, x cubed, x to the fourth, and so forth. So we have x to the n, because when I plug in 2 for n, we'll get x squared which is like so, x cubed, which is n equals 3, and so forth. And then we also have 1 times x, then we have 1 times 3, then we have 1 times 3 times 5, and so forth. So I'm going to rewrite it as 1 times 3 times 5. You can go as many as you want. But let's just write 1 times 3. And so the pattern for this is 2n minus 3. Because whatever we plug in for n, when we plug in 2 for n, we'll get 1. When we plug in 3, we'll get 3. Plug in 4, we'll get 5, and so forth. So all odd values. And then on the denominator here, notice we have 2 squared, then 2 cubed, and then 2 to the 4th, 2 to the 5th, and so forth. So we'll get 2 to the n times, and then we have 2 factorial, 3 factorial, so it's going to be n factorial. And so this is the final answer for the power series, given the binomial series. So now for number 2, let's say we have x over the square root of 4 plus x squared. And so in order to get this to look like 1 plus x raised to the k power, I'm going to first factor out a 4 from the 4 plus x squared. So we'll leave the x up top, and we'll get 4 times 1 plus x squared over 4. And instead of writing the square root, I'm going to write it all to the 1/2 power. And so we can distribute the 1/2 to both of these. And so 4 to the 1/2, or the square root of 4, is basically 2. So we'll get x over 2 times 1 plus x squared over 4 to the 1/2 power. So now I can treat x over 2 like a constant and bring it out to the front. And then I'll move the exponent up. So we'll get 1 plus x squared over 4 to the negative 1/2 power. And so now we have it in the form of 1 plus x to the k, where our k value is negative 1/2, x over 2 is just a constant, and instead of a positive x, we have a positive x squared over 4. So if I were to rewrite the binomial series here, notice x over 2 is a constant, so I can bring that out front and treat it like a constant. So x over 2 times the series from n equals 0 to infinity. Now our k value is negative 1/2. We have n on the bottom, and instead of x to the n, instead of having a positive x, we have positive x squared over 4. So we're going to replace x squared, or we're going to replace x with x squared over 4. So it's going to be x squared over 4 all to the n power. And so now what I can do is expand the binomial given the formula. So if I were to rewrite it, we'll have 1 obviously as the first term, and then plus k. Now k is negative 1/2. Instead of having x, remember, we have x squared over 4. So it's going to be k, which is negative 1/2 times x squared over 4, plus negative 1/2 times k minus 1, so negative 3/2, times x squared over 4. Now the entire thing is squared this time, over 2 factorial, and then plus negative 1/2 times negative 3/2 times k minus 2, which is negative 5/2, times x squared over 4 to the 3rd power over 3 factorial, and so forth. Now don't forget that we do have x over 2 outside of the series, so once I simplify this entire thing, I'll multiply the entire thing by x over 2. So if I were to simplify here, we get 1 plus, well actually there's a minus here, so minus x squared. Now instead of multiplying 2 and 4, I'm just going to leave it as 2 to the 1st times 4 to the 1st. And so for the next term, the negatives will cancel. So then we'll get 1 times 3, positive 1 times 3, times, now x squared squared is x to the 4th. And then on the bottom, we have 2 times 2, I'll rewrite it as 2 squared, times 4, which is also squared, so 4 squared, times 2 factorial. And I also forget, I gotta put the 1 times here. So 1 times x squared, then we have 1 times 3, so I can recognize the pattern. So next one we have 3 negatives, so there's gonna be negative 1 times 3 times 5 times x squared cubed, which is x to the 6th, over, now we have 3 2's, so we have 2 cubed, times 4 cubed, times 3 factorial, and so forth. So now I'm going to multiply it by what we have as the constant outside, x over 2. So So then to evaluate, we'll get x over 2 minus, now whenever we have the same base, we can just add the powers. So then we get x cubed, or 1 times x cubed, over, now 2 times 2, 2 squared, times 4, plus 1 times 3 times x to the 5th, over 2, now this time is 2 cubed instead of 2 squared, times 4 squared times 2 factorial, minus 1 times 3 times 5 times x to the 7th over 2 to the 4th times 4 cubed times 3 factorial, and so forth. And so before I write the power series here, notice that these numbers here, 1 and then 1 times 3 and then 1 times 3 times 5, that's not going to be in front of the first term, so I'm going to leave the first term outside of the series since it does not follow the pattern. So I'll have x over 2 plus the infinite series. Now since we're skipping out on the first term, we're going to start at the second term. So if the first term is n equals 0, the second term is going to be n equals 1. So 1 to infinity. And so notice we have an alternator, and the first term that we start on the series with is negative. So I'll write it as negative 1 to the n. Since if we plug in 1 for n, negative 1 to the first is still negative. And then notice we have x to the cubed, x to the 5th, and then x to the 7th. So I can rewrite that as x to the 2n plus 1, because it's always going to be odd powers. And then notice we also have 1 and then 1 times 3, and then 1 times 3 times 5. The next one is 1 times 3 times 5 times 7, and so forth. So I'll rewrite it as 1 times 3 times 5. And so the common pattern here is 2n minus 1, because it's always going to be those odd numbers. Because if we plug in 1 for n, we'll get 2 minus 1, which is 1. If we plug in 2, we'll get 4 minus 1, which is 3. If we plug in 3, 6 minus 1 is 5, and so forth. And so on the denominator here, notice we go from 2 squared to 2 cubed to 2 to the 4th, and so forth. So I'll write it as 2 to the n plus 1. And then we have 4 to the first, 4 squared, 4 cubed, so that's just going to be 4 to the n. And then we obviously have n factorial, because it goes from 1 factorial, 2 factorial, 3 factorial, and so forth. And so now if I were to simplify this just a little bit more, 4 to the n can be rewritten as 2 squared to the n, or 2 to the 2n power. And so when we have 2 to the n plus 1 multiplied by 4 to the n, which is 2 to the 2n, since they have the same bases, I can add the powers. So we get 2 to the 3n plus 1. So if I were to rewrite the series one more time, the power series is going to be x over 2 plus the series from n equals 1 to infinity of negative 1 to the n times x to the 2n plus 1 times 1 times 3 times 5. And the common pattern here is 2n minus 1 all over 2 to the 3n plus 1 multiplied by n factorial. And so that is the final answer for the power series of the given binomial.